So since we were in the predictions game, I decided I'd enter into predicting how the models will actually change with time. And before I came, I actually spoke with a number of people at GIS about what they were doing, what the timelines they thought were, and I myself corrected them for what I think are the unrealistic nature of their timelines. So
you multiplied by a factor.
and change to the next higher unit, that's what they say. Okay, and so this first, so the way this is broken up, X, Y, and Z relate to what I believe will be, and I have this as a GIS perspective, though I'm not guaranteeing that everybody at GIS is going to agree with this for sure. But what would be in the model with some confidence by 2009? Some of these things are in the model now, but there's absolutely no confidence in them. They haven't been verified, they haven't been quote-unquote tuned or calibrated. And so X is 2009, Y is 2015, Z is 2021, and when you say 2021, it could be any time, basically. In fact, I was thinking of leaving this bar off so that it implied that. Okay, so what GIS will have in the next version of their model is clearly finer horizontal and vertical resolution, but not on the same order as we were discussing for the short-term predictions. My guess it'll be like 2 degrees or 2 by 2.5. The vertical levels that people are talking about for the standard model are something like 40 or 45. Now, we already have higher resolution versions than this that we're running in a supplementary fashion. We have a 150-layer vertical resolution version that we're running for tests on QBO and things of that nature. My guess is that in this time period for 2009, these versions with higher tops will be supplementary models. And what I mean by that is, if you're going to investigate some issue, you'll run it with that model, but it won't be the standard model that you use for the multiple ensemble runs. There is a version, actually, of the standard model that has a top very high up, but nobody's really worked on it. It's not really ready for prime time. In any event, these tend to be much finer vertical and horizontal resolutions than would be run for the multiple ensemble experiments. Dynamic vegetation. So I break this up into 3 categories. One is Nancy Kiang at GIS is working on a dynamic vegetation scheme with a number of people around the country, actually. And it has several different components. One is it is to be the land surface scheme, at least as far as the transpiration and so on is concerned. So it has to operate on hourly time scales, has to give seasonal variations of the vegetation health and interannual variations of the vegetation health. I'm pretty confident that that's actually going to be in and have some degree of confidence by 2009. For things like succession, in which you then sort of change from one vegetation to another type in place, I put down some confidence by 2015. I don't think by 2009 there will be anything like that, and I can't even guarantee this. And for things like movement or migration of vegetation from one box to another. So I said to Nancy, well, how do you know? People have said the landscape is fractured, things aren't going to be able to move. She said, well, we just give complete distribution of seeds everywhere, basically, and what can grow can grow. And I don't know what the reality of any of that is, but I put this down with some confidence by 2021, but it could be. It's going to be very hard to get data to compare with this. What people have tried doing in some of the vegetation model assessments previously is look at the deglaciation time period and see how the vegetation changed with time. But if you know that field, you get very diverse results depending upon what model you use, and northern pines versus southern pines, and there are all sorts of things. Carbon cycle, atmospheric chemistry. There are versions that run right now with the standard model. I don't believe they will ever be standard in our model. I think that the experiments we've done a lot of experiments with Harvard on this, and the advantage you get, and I heard this idea that when weather is an influence, you really should run it coupled, and it is run it is run coupled in supplementary models, but the standard model, I think the feeling is that for anything that has realistic chemistry, it's too big a computational burden for what you gain from it. So for example, it can be run in a supplementary form in a time slice to say what how tropospheric ozone changes with time. And then in the standard model, you just put in those tropospheric ozone changes with time. Not perfect, but this is my guess is what would happen. Complex aerosols, we are doing work with John Seinfeld and his 180 tracers. There's a lot of work at GISS on aerosols and aerosol modeling and aerosol observations. Again, my feeling is that at least on these time frames, they will be supplementary versions of the model. And in terms of the very complex aerosol modeling, even the supplementary versions aren't going to be here for another 10 years to run. I mean, John Seinfeld really can't run for more than a few weeks in the version of the model he's using. And there's so many free parameters here. You have to try to understand aerosol size distributions. Okay. Complex clouds, there actually should be a line in between here. Complex clouds, and by this I mean trying to really get the size distribution of the droplets and things of that nature. So I had a long talk with Tony Del Genio about that and put down 2021, and from his perspective, even that is pretty optimistic. We just don't have the data for it. There are just too many different things you can do, and clouds are tough, and convective clouds versus stratiform clouds. Different stratiform clouds in different regions, obviously CCN differences, land and ocean.
So you're not going to couple that to your aerosol, your
If,
complex aerosols?
Well, I doubt that that will ever happen in the standard version of the model. But it will happen in supplementary versions, this coupling. I think once the complex clouds are in, they will go in the standard version. That it's important enough for climate change that they will be in there. Everything we've done with clouds, specifying clouds, crudely varying clouds, cloud liquid water budgets in a mass sense, all of those things have always gone as quickly as possible into the standard version of the model. But in terms of running it with some confidence, that's another story. I'm sure we could get something in by 2009, but have absolutely no confidence in it. Ice sheets, this will always be offline. There are really questions because of spatial and temporal discontinuities between how you force an ice sheet. You know, the problem is that GCMs have to be run at very fine resolution, otherwise they get too much moisture on land for the big ice sheet regions. A number of people at GISS really want to do sea level changes, and they're frustrated by not being able to say something about the ice sheets. So we will work on supplementary versions of the ice sheets, maybe asynchronous coupling, maybe something. But again, I don't think anything with any confidence. And again, 2021, who knows? Really.
Given Jim's recent proposal, he's really pushing this greenland ice sheet destabilization. It's interesting that hasn't moved up higher on the agenda.
When I talked with Jim about this, that was the first thing he mentioned. Ice sheet modeling. So the 2021 delay is because we don't really know how to do it. How frozen is the ground? How much of runoff really infiltrates all the way down through the crevices to the ground? And we know any of this. So you could do these models, but what would you believe?
Well, are you going to do them and then not have confidence in them, or are you just?
Yeah, I think these will be being done. But my criteria for this graph is that you have some confidence in it, because you can do anything, but what meaning does it have? Groundwater hydrology. These are longer term processes, but aquifers and things like that. Water resources are a big issue independent of climate change. And there is a push to start looking at this issue. And again, I don't think the push is like the waterhead itself isn't high enough to get it up on the graph of importance, but people are starting to look at it, and I would give it, again, another long-term result.
Actually, it's interesting because we didn't talk much about that in this meeting. Is that just because there's not much work going on in this in our kind of modeling community? I mean, there's obviously a lot of people that do groundwater and hydrology, but
there are some limited modeling studies that are actually starting to look at the how impoundments and irrigation and land use are linked. But there's not, and there are some spatially resolved models that can distribute the water, the rhesus class of models. But I think we're just starting to think about these sort of social, the human water. But I think that getting your groundwater is going to be important for your water budget in many ways, in a lot of places, the high latitudes. because as those peats and those organic soils start drying out and the water table starts rising, the classic example that's happened in Australia with the salinization of the whole Murray-Darling Basin from irrigation, making that whole basin just agriculturally dead. And so there's that sort of example, and there's the high latitudes as you're changing the water table. What the balance between, it's about a 60% saturation between methane versus CO2 emissions. So that's probably why a lot of people are looking at that, both for human and sort of not really non-human but climate impacted areas. But the impoundments and that sort of thing, there's just starting to be, modeling activities along
You
those
can
lines.
imagine a whole set of coupled interactions because this is going to come
Yeah.
up in the Denver area because there's all these new subdivisions that are drawing up groundwater. That's their only supply of water, which is going to be gone basically in 20 years. So that means there's going to be a big rush to buy up more agricultural water, which means agricultural land will then transfer to something else, and then you get a whole land use kind of thing going on.
It's a good one for integrated assessment models.
Yeah.
So do you include in that aquifers?
Yeah.
Yeah.
For resolved convection, obviously small scale, 900 static. It's possible GIST will never run resolutions that high to do it. And saying 2021 may be the equivalent of saying never, but certainly not going to be soon, that's for sure. And in the same context, gravity wave generation. Models use gravity wave parameterizations. If you do stratospheric model into comparisons, to some extent they differ by what the gravity wave parameterizations are. Theoretically, if you're running very high resolution models, non-hydrostatic models, you might be able to, depending on your numerical scheme, get gravity waves generated and have what they do in the stratosphere, maybe even upper troposphere, directly resolved by the model. We require very high vertical as well as horizontal resolution. And again, if it ever happened, I think it would be a standard component of the model, as would the resolved convection be. But it's not going to be for quite some time.
So in your link you mentioned 150 levels.
Yes. Yeah.
Were you seeing any of that?
Yes, we do see changes in gravity waves. And also, I'll get into the next section in a moment, but a lot of models filter their wind fields in the dynamics. And when you do that, of course, you lose a lot of the value of that higher resolution in terms of gravity wave generation. So we've tried running it without filters, which you can do. The precipitation field gets much noisier because there are numerical things that you're filtering is really getting rid of, numerical problems. So the hope is, and I'll get into that in a moment, that when you get to these very fine resolutions, your dynamics will somehow be stable enough not to require this degree of filtering. I don't think there's any guarantee on that. In fact, the whole issue of dynamics I'll sort of get to in a moment.
So kind of what you're targeting for your new kind of standard resolution is around 2 degree class model, right?
Yeah, 2 by 2.5, I think, will be the standard one. And some components like this, I think, will definitely be in there. And some of the other components as supplementary will be there. There's not a whole lot of change between the short time scale and the longer time scale, except for some of the vegetation concerns. Carbon cycle, we are already running a carbon cycle. I don't believe it will not definitely be online in the standard model, but it could be used to inform the standard model of how if there are any projections independent of the carbon cycle, that those projections should be changed. Again, in an iterative manner.
Well, the type of experiment we were talking about where you specify concentration,
Yes.
you could actually do that in that
exactly,
way.
right. Yeah.
David, could you characterize the computing ability assumption that's kind of behind?
Yeah, there are, obviously, these do require large computing increases in time.
So
We've actually had quite strong increases in our computing capability over the last 10 years. Whether that will continue depends upon NASA's largesse and actually what NASA's focus is going to be. Are they really going to turn away from the Earth system? In which case, I don't know. I mean, that's another scale of predictions I can't make here, actually.
So you're not planning to develop a kind of gravity wave generator or something that
We have gravity wave parameterizations already. In fact,
Yeah.
quite complex ones, but how good are they? I don't know.
parameters.
Right, there are schemes like at Toronto that have put in very sophisticated gravity wave sources that take a lot of computer time. I don't think we're going to do that. We'll stick with either the relatively crude parameterizations we have, or if ultimately we get down to that level, we'll try to let the model do it itself, which obviously is sort of best. Yeah, and the dynamics might always be an issue.
It may be possible to derive some statistics about gravity waves and large-scale field.
Yeah, I mean, it's tough to observe them. I mean, Richard Lindzen pointed out that the gravity waves that break in the stratosphere at certain regions in the stratosphere are actually too small to see in the troposphere. So how do you find the sources? People have tried to do trajectories, you know, convection, shear, flow over mountains. These are the standard.
Uncertainty is sources.
Yeah.
I mean, the breaking process is not. It's actually things are models are not actually that sensitive to the details of the breaking process.
Exactly. We have a very different scheme than the one you use, Norm. But we tried your scheme and didn't hardly made any difference.
Yeah. Paper published recently by McLanders and Sonocovers. They tried a range of schemes. And they basically concluded that it wasn't the breaking formulation that was the significant factor. It was the sources.
You're essentially, well,
It's the specification of the source spectrum that was the most significant problem.
And with our parameterized sources, we do find that climate change does change the gravity wave sources. But how good are our parameterizations? And so it'd be better if the models could do it directly, but I don't know. So that was the Earth system model. And so now I'd like to make sort of a few comments on predictions for the AO model itself. Now, obviously, some of these general categories overlap what we've had for the Earth system model, but some don't. So this is perhaps even more.
I mean, are they going to be run? Is it going to be run for a different class of problems? Is that why we make this distinction?
No, only because there's some components like dynamics, atmospheric dynamical routines, which aren't under the Earth system model categorization. It's just to fill in, like boundary layer, which wasn't discussed previously, and so on. So these are the components that are in the standard version of the model or will be in the standard version of the model, as opposed to a number of those other guys that are going to be supplementary runs. Solar radiation variations, we now actually do run normally with solar radiation variations. And you know, the source mission is trying to determine what the distribution of those variations from solar max to solar min are as a function of wavelength. And UV has been known for quite some time, but visible and near IR have always been issues. And my guess is that, okay, so this is when it will be there. And I'd like to, when will there be significant improvements in the subroutines? That's what this table is, and that's what the X is. Not sort of marginal, but really significant, almost quantum leap types of things. And so what we do with solar radiation variations now is basically we just vary the total solar irradiance. And that sort of has implications throughout the whole spectrum. But if we have continuing solar radiation observations and we can really see what happens to the visible and near IR for what would then be like 4 cycles, 3 to 4 cycles, then actually we would put that in as a standard. Atmospheric radiation, Andy Lasis does the radiation at GISS, and he uses this complex scheme which sort of bands together the wavelengths with the strongest absorption as opposed to doing a band model on frequency. In any event, he compares everything with the line-by-line codes that he runs. And if computers get fast enough, I think eventually he would like to run the line-by-line code directly. Again, this is a big computer time issue. It's not, I mean, he can do it right now. Obviously, he runs the line-by-line code now. And there are improvements that are done in these line-by-line codes as over the years. Not great changes, but people do make small improvements. So this is what he would like to do. Whether the computer time is available, I don't know. Right now, actually, the atmospheric radiation in the version we're running takes about 25% of the computing time. When you go to very fine resolution, it takes less because the dynamics take so much more, depending on what type of architecture you're running on. This is still...
Is that because you don't run it on at the same resolution as the dynamics?
No, because as you point out, that when you go to finer dynamics, your time steps get smaller.
Right.
And the dynamics is...
So you don't run it at the same temporal resolution?
Yes, yeah, right. 2 minutes for some of our dynamic time steps, and half hour actually is the radiation time step. Cloud cover. The people at GIST, Bill Rostow and Tony Del Genio, are quite caustic in their comments about cloud resolving models. And as Bill Rostow says, they don't resolve clouds. They don't have any microphysics in them. They don't know anything about clouds. All they do is they're really small scale. But I think what will happen is that as more and more people run cloud resolving models, at least some components of what the cloud resolving models are saying will go into the parameterization. Whether the cloud resolving models themselves go in, that I'm, at GIST in particular, I'm less certain about. But it's not out of the question. Again, it's a computing power question. I think this idea of having droplet-sized distributions in your clouds, which now gets into the cloud microphysics as well, that is a goal. And again, remember, we had it at 2021 previously, and will it really happen? I don't know. Aerosols, again, the big deal about the more extensive aerosols is that you do, obviously you're not just using mass, but you're using particle number distribution as a function of size and interactions between the different sizes and so on. Convection, again, 2021 for the resolved. For large-scale rainfall, if we actually had droplet size, then you could look and see, can you build a raindrop with coagulation and collision, and can you get the rain to actually fall? And that's a real complicated process. It involves the Earth's electromagnetic field, which acts on the polar molecule. But maybe you could do some parameterization. And there are models that obviously now work on trying to get large-scale rainfall from cloud particle sizes. So again, I have that at 2021. The dynamics, we have a long history of running different dynamics in our GCM, and you get very different climates with the different numerical schemes, and that does not change so far as you go to finer resolution. But it may well be that when you get down to a really fine resolution scale, then the difference between the different grid schemes, for example, won't be such an issue. But as it is right now, in the IPCC submissions, Gary Russell put in his atmosphere-ocean model, which is on a C grid, and the 2 B grid models are there as well. And a lot of their aspects are different. In fact, almost everything you look at in terms of the momentum or energy forcing does have what scheme you're using, numerical scheme, has an impact on it. The mountain, the flow over mountain, I mean, just about everything when you come right down to it. So the hope is that when you get to fine enough resolution, all of those issues will go away. You're solving the differential equation better. Where would we be without hope in this field? So, and also, if you really got to finer resolution, then you could do things like maybe you could deal with the filter in a better way or something. Atmospheric boundary layer. We're running a complex scheme now. It's a second or sometimes 2.5 order closure scheme with non-local turbulence, so the turbulence can be advected. I don't see any big changes in that. This guy, Vittorio Canuto, has his own turbulence scheme, and it's his group that's actually doing this. So I talked with them, and the only thing I can see ultimately is if we really go to LES processes, the large eddy simulation, which people use for comparisons to these schemes since they don't have any data to compare to. I think if we had enough computer power, this could start to be worked on at any rate. I put down 2015, but there's a strong presumption on computer power for that.
Running an LES boundary model coupled.
Yes, if this scheme were available, it would definitely be run coupled. There's nothing we're really doing offline for the boundary layer. All the boundary layer stuff immediately goes online. Atmospheric surface layer, I differentiate this from boundary layer because one of the untold secrets is that, like Canuto, when I talk to him about the surface layer, he says, I don't do surface layers. The surface layer is between the boundary layer and the ground, but it's the layer that gives you the surface air temperature, surface wind speed, surface specific humidity. How do you get the surface values from the boundary layer values and the ground values? And that is sort of an art that people have stayed away from as much as possible. Sometimes you just extrapolate. Sometimes you do energy in equals energy out balances. Nobody at GISS is working on it right now. I continually sort of push the issue that when we did our model development from Model 2 onward, changing the surface layer had a tremendous impact on everything you can think of, the momentum fluxes, the eddy energy, how you actually made that calculation in an iterative way with the momentum balance. I mean, it's highly nonlinear process. Right now we're using the so-called similarity theory. My hope is that if this actually happens, then it will have ramifications for that. And I think that would be the case. Land surface vegetation, again, interannual, succession, migration. Soils. Right now what GISS does for the soils is it has a number of soil layers. Standard version is 6 soil layers. And moisture moves up and down based on texture discriminations, Darcy's law, with conductance coefficients based on is it soil, is it sand, is it clay, etc., is it silt. Other people and other models actually sort of assume that the structure issues dominate vertical transport, like wormholes and root holes. So they have exponential decreases of this moisture conductivity with depth, sometimes the same everywhere all over the globe. Well, we've actually done some work on structure issues, karst topography, for example. There's much greater flow through of moisture there than in other regions, and there's an awful lot of the world that has karst topography. The Southeast US, for example, has a lot. But generally, people haven't put this in. So I talked with the hydrology people, and they are very reluctant to do something that, I don't know, maybe they feel this is too sort of data intensive and mechanical, and they rather do things that are more creative. But eventually, hopefully, we will do better soil structure. Also, there are many other things associated with this whole thing. For example, how do you do runoff? Well, in our model, we have the slope of the topography based on a high-resolution topography scheme, and that gives us a water velocity because it's sort of running horizontally. And this is for surface runoff and underground runoff. And you're given a certain velocity, and when do you get runoff? Well, when it gets to a river. But how do you know when it gets to a river? Well, you need to know what the spatial distribution of rivers are. So in the GISS model, runoff is done 10 meters. That's the spatial distribution. So we have the speed of horizontal movement and 10-meter difference, and then we see how long it takes for the water to get to the rivers, and that tells us when the soil moisture has entered the rivers. 10 meters is clearly not the right value everywhere in the world. Desert regions, rainforest. It has been impossible to get the group to actually sit down and try to make this calculation more reasonable. Maybe because they feel the whole thing is not really reasonable in the first place, and they don't want to spend more time on it. But there are a number of issues related to the soil and vegetation structure for hydrology that could be handled a lot better if you could get people to have enough incentive to do it. Sea ice, we discussed briefly that more thickness distributions within a grid box. People are running that already. Judy Curry has a number of things like that. And how you handle brine and brine pockets in sea ice. I'm pretty confident that this stuff will actually be in by 2009. I don't know that it'll be right, but it'll be in. And oceans, with a lot of computing power and very high resolution, eddy resolving ocean models, I mean, that's potentially a goal. Whether it's really necessary or not, I don't know. But as long as I put it out to this time frame, I'm sort of pretty safe. Okay, the last thing I want to talk about is how do you make decisions based on what degree of complexity is actually needed in these models? And this is a continual tug and pull in modeling, because people who are working on these offline models, everything is sort of important. They want to do it right. On the other hand, in the GCM, if everything is being done right in this model and it takes 10 times the computer time of the atmospheric model doesn't want to use it. So how do you make the decisions? It has been my observation that if you start an offline model for a new process that hasn't been in the GCM previously, it takes 5 years to bring it up to the level at which it can be put in the GCM, at which point a lot of determinations on complexity have been made in that offline model. But the offline model specifies things, like for hydrology, it'll specify the specific humidity at the surface, or precipitation locally, or surface air temperature. It's not done interactively. And the complexity that you feel is necessary in the offline model, is that going to be the same complexity as in the online model? And my experience is it is not. And often the complexity in the offline model is too great. When you put it in the online model, you get a lot of negative feedbacks that even if you leave something out, it doesn't change things that often. So to try to get some degree of interaction, people are going to single column models, in which now they have the whole atmosphere interacting, say, with the surface. And then when you change something like the convection scheme, you can get, at least within that column, interactions between the different components to some degree. Well, you really can't do this in all diverse regions. I mean, this is a way, and this is the way people are actually trying to understand the degree of complexity needed. But ultimately, you have to put it into the GCM to make that determination. And then when it's in the GCM, who does the evaluation, and how do you run the GCM? If you run it with specified sea surface temperatures, then what you've put in, which may have very little impact because everything's controlled by those specified sea surface temperatures, might have more of an impact if you allowed the ocean temperatures to respond. Also, it might have a bigger impact in an equilibrium simulation. So do we do it for climate change, or do we do it for the current climate distribution with specified SSTs? Generally, that's what it's done, with specified SSTs. Who does the evaluation it's a human issue, because, for example, if Tony Del Genio is putting in a convection scheme, and he says, you know, this convection scheme matches the heating profile in the gate observations in the North Atlantic better. And Jim Hansen looks at it and says, with all that added complexity, it didn't change the climate sensitivity one iota. We don't need all that complexity. So who does the evaluation? Is it the person who put it in, or somebody else? And that is an issue. And of course, assessment should be made in terms of impact on variability and climate change rather than just climatology. And there's just one last issue here. So an alternate approach is to put the whole thing in with all the complexity, and then sequentially reduce the complexity so that you're running quicker versions of the model, until you get some point where you say, hey, now it's unacceptable, so we'll just leave it at that level. And the turbulence boundary layer is an example. So the guys doing the turbulence boundary layer said, we need 20 levels in the lowest portion of the atmosphere for our second order closure scheme. And Jim Hansen said, forget it, you're not getting 20 levels. We're not going to spend the computer time on that. So they put it in, and then they tried reducing the levels and doing little tricks to get sort of implied things between the levels and so on. And so now I think what they have is, it's implied, but it's like 6 or 8 that they're using. But they're not happy about it, frankly. And I make the comment that it goes against human nature to accept less than the best. And especially if these guys have spent 5 years making the model as perfect as possible, and then it goes into the GCM and it's not what they think it can do, that has morale impacts. And again, we have the same evaluation problems. When you're making that decision of what is good enough, are you doing it with specified SSTs in a very localized experiment, or is it for climate change and climate variability? The practical approach, which I must say works at GIST most of the time, is that Jim says to them, you can only have this much computer time, and you've got to stuff your parameterization in. And so an example of that would be the infiltration scheme in the ground, in the soil. Now, you know what happens in the soil is that as you wet the topmost layer of the soil, that wet soil has a greater conductivity, so more moisture can infiltrate. If you use long time steps or thick layers, the soil doesn't get very wet, and therefore it doesn't infiltrate. So these guys in the soil wanted to use 20 layers in the soil, and Jim vetoed that. Way too long computer time. So what they've done is the way it's set up is that only in conditions when it would seem to require more layers are the more layers added in. They're added in so asynchronous, they're added in aperiodically. When there's a heavy rainfall event, there'll be more layers added in to better do, and then things will then be averaged out to the standard 6 layers. And when it's not raining, it'll just be 6 layers. So that's sort of an approach that people are trying to use now to add the complexity when needed, but not have it run all the time. And again, in the end, this is often used. I'd say that the people who are doing this are concerned with the quality of what they're getting, and they won't sort of just accept these blanket statements on how much time they're allowed. They'll make vicious, ferocious arguments that you're really affecting the quality. But so obviously there's a compromise. Yes. Well, again, you test it, but on what? Equilibrium climate, specified SSTs, local impact. Okay. And another thing is, I found, as far as GISS is concerned, that a number of these decisions on what degree of complexity would be allowed were made with computing power at that point in time. But now computing power is greater. And so do you go back to these people and say, okay, you can add the complexity in? And that generally isn't done. And it probably should be done. That if people know how to do things better, they should be able to do it better when computing power goes up. A lot of times these schemes are thought of as closed and the people then move on or something, or try different schemes. Anyway, thank you.
So what that requires is a dictator.
Well,
who
right.
has decided the certain amount of times for parameterization.
There are some process. I mean, there's
And that would vary between dictators.
Or what we have, for example, at GISS, we have people who have different models, and they don't like the choices that Jim made. And so we have our own versions of the model, which we will use for experiments we think are more appropriate for those models to be running as opposed to something he's running. So.
It seems to me that some of the issues also come down to what you're trying to apply, what problem you're trying to apply it to. For example, I mean, we found that for convection that the Clausius-Clapeyron relationships are such strong constraints on water vapor and temperature, for example, that you can get away with one particular scheme for heat and moisture, but you couldn't live with it necessarily for moving tracers around. And similar things go for carbon cycle and boundary layer parameterizations, for example. So it's interesting to me to think about, well, how do you guys deal with these issues? For us, we're always trying to think of the most complex problem we might try and solve, and to design the parameterization so that it's suitable for that problem, even though it might be overkill for some.
Right. I would say that Jim has become a little bit more open to that idea as the idea of regional impacts has grown in importance in his mind. But in the past, it was probably, does it affect the radiative forcing? If not, no. Or it's simple. Or it's simple.
There's some virtue in having highly complicated models that can be run in a GCM. I mean, think of the boundary layer. And I know what Canuto's work. I've read a lot of his work. And of course, he tries to be very consistent and pure, if I can put it that way, and I sympathize with that. But at some point, it's possible to parameterize quite a bit of what is actually done by going to, say, a higher order moment closure, which is very complicated and costly. But what it gets for you, on average, much of that can be parameterized.
I agree. In fact, a lot.
There are cases where it just doesn't work, and those are the tough cases, but many of those cases are there.
I think this would be Jim's point too, that a lot of the complexity is of second order importance most of the time. And so do you really want to burden the whole model with it all of the time?
Well, but there are clever ways,
Yeah,
capturing
clever.
some of those features.
The other problem you get also is competing schemes, where, like in the case we've got right now, a cool comparison going on with these different carbon cycle parameterizations, and so then you have to decide which version goes into the model, and we endlessly have problems making those decisions because everybody has different criteria, and depending on which criteria you use to evaluate, one looks better than another, but then another one outperforms that one on some other criteria, and that seems to be an endless problem with these, especially with these larger, more complex models. We have different groups working on trying to get different things in the model. I don't know, and nobody's come up with a good solution to that yet, I don't think. Except Peter Jensen can figure that out.
Also, I felt like this one where you do the more complex model and then reduce the complexity down in a rational manner. We generally don't have enough time to do that in at least a rational manner.
Well, what happens with us is that in order for it to go into the standard model, that has to have been done already. That it's run in the supplementary model in complex form, and then in the supplementary model they reduce the complexity. And then when they say this is as simple as it can be, then it gets put into the standard model. So the standard model never has the ultra complex scheme in it.
Provided it satisfies the criteria for cost.
Yes. Yeah. I mean, I'm sort of blaming Jim on about all this, but in fact, a lot of people like to do a lot of runs, and so it's not only him.
Okay, thanks, David.